Welcome to Unit 4, Lesson 1 on vibration and waves. By the end of this lesson, you'll be able to demonstrate an understanding of vibrations, waves, and particle behavior in different media. You'll know you've been successful when you're able to describe in detail the vibrations, waves, and types of waves, longitudinal and transversal. You're able to investigate the behavior of the particles in different media. You're able to solve problems related to the topic, and you're able to apply the concept to solve problems related to your daily life and to make connections. So, you see many objects that move back and forth in motion. For example, some movements on a windshield wipers or the pendulum in a clock are all back and forth motions. The wipers and pendulum repeatedly move back and forth along a fixed path, resulting in a cyclical motion. Many of these cyclical motions are more rapid and therefore difficult to see. So for example, if you put your hand on a speaker of an operating stereo system, you'll feel it shaking with the music. The walls of the speaker are moving back and forth, but they're moving too fast and too slightly to be seen under normal conditions. So these objects move back and forth about a middle point. This is called an equilibrium point, as we see in the image on the right, or rest position. When the motion stops, the object returns to this point. So if you stop the pendulum that's swinging in this image, it will hang straight down at the equilibrium point. So you'll also notice that the equilibrium point is halfway between the maximum distance of the pendulum swings. That is known as one vibration or one cycle. So a vibration is the cyclical motion of an object about an equilibrium point. Vibration, in a general sense, is anything that switches back and forth, to and fro, side to side, up and down. It's all forms of vibration. One vibration or one cycle of the pendulum is one complete vibration. Particles that are part of a material, like a drum head, if the particles in the drum head are disturbed, such as when you beat the drum, the vibrations created by the disturbance are transferred throughout the material. So this transfer of energy through a material by a particular vibration is called a mechanical wave. So a mechanical wave, again, the transfer of energy through a material due to particle vibration. And the medium is the material through which the mechanical wave travels. It's the material. It can be a solid, a liquid, or a gas. So mechanical waves need matter, medium, to travel through. A vibration is able to travel through a medium because each molecule in the medium is connected to the neighboring molecules by intermolecular forces. Mechanical waves are one of the most efficient forms of energy transmission in nature. So when vibrating, a medium tends to gain or lose very little energy. Thus, a vibration can continue for a long time in some media. A vibration is able to travel through a medium because each molecule in the medium is connected to the neighboring molecules by intermolecular forces. These forces allow the distance between the atoms to increase slightly without losing energy. This molecular property of a medium allows a mechanical wave to be one of the most efficient forms of energy. It is the net motion of the particles that cause a vibration. So net motion is the displacement of a particle over a certain time interval. The particle may follow a complex path, but the particle's net motion is how far it has moved in a straight line distance from its starting point to its finishing point. After a wave has passed through a medium, the particles return to their original location, and ideally there's no net motion of the particles when they have stopped vibrating, so their net displacement is zero. So therefore no work is actually being done on them by the wave, no energy is lost by the wave, and it can continue indefinitely. So we can see that this is what's happening in the figure below. So this is, on the right, is a picture of a boat. And it's at the top of the wave, and after the wave has moved past it, then the boat will return to rest at normal. So the boat goes up when the wave comes and then goes down after the wave passes, but ultimately the boat does not move with the wave energy. It doesn't move left or right, it just goes up with the water and back down. So there's no work done or no loss of energy. So particles behave differently in different media. So the particles of the drum head, in this case on the left, vibrate and transfer their motion to particles beside them. This allows the wave energy to move through the medium. So you can think about this as if I sit on one end of a mattress and at the other end you place some objects such as textbooks. If you bounce on the one end of the mattress, the objects on the other end will move. So this is the material in the mattress is all connected. So a disturbance at one end is transferred to the other. Remember that particles are always in motion. Solids, they're vibrating much closer together than liquids or gases. We saw this in an earlier lesson. And this is because of our thermal energy. So remember that thermal motion is the motion resulting from thermal energy. It's random and does not produce a transfer of energy in the form of a mechanical wave. So instead, the medium has to be disturbed by vibration to set up a mechanical wave. And that's what's going on in B. So this is what the particles are doing of the drum head. So the particles in the drum head are vibrating and they're going to transfer their motion to the particles beside them. And this is the way that the energy is able to move through the medium. A medium's effectiveness at transmitting vibrational waves depends on its structure, its molecular and mechanical structure, its density, and even its temperature. So in this case, we have an image of particles moving in a solid, a liquid, or a gas. So we can see that on the left, for the first one, it is microscopic particle vibration in a solid. Second one is a liquid, and the third is a gas. So solids and liquids are usually more effective at transmitting vibrations than gases are, because the particles are closer together and they're moving in a much more specific path. Remember, in a solid medium, the atoms are held securely in a crystal formation by strong intermolecular forces, so they can only vibrate slightly as the disturbance passes through the medium. If the medium returns to its original shape after this disturbance, the medium is said to be elastic. Most solid media have this property. Even very rigid media, such as steel. So in general, rigid materials transfer mechanical waves more efficiently than less rigid materials. Thus, mechanical waves in rigid materials last longer, they go faster, and they go farther than they do in less rigid media. So during an earthquake, for example, vibrations through rigid media like rock can be transmitted thousands of kilometers from the source. This is why you can feel an earthquake kilometers and kilometers away from where the actual epicenter is. So reversely, in the less rigid a medium, the less efficient it is at transferring a vibration. So for example, a pillow will disperse more energy through absorption, so the vibration quickly weakens. The particles aren't necessarily as close together, and so they're not able to pass along that wave that energy as effectively. So liquids and gases are classified as fluids because they are materials that can flow. In liquids, the molecules are not in a crystal formation, but are still very much in contact. So liquids are very efficient transmitters of sound. For example, sound travels almost 5 times as fast and much farther in water than in air. So think about hearing whale sounds from hundreds of meters away, and individual molecules in gas are much further apart than they are in liquids and solids. So gas is the least dense state of matter, and they rely on translational molecular motion, so the straight line motion of a molecule. This motion is typical of gases because the particles in liquids and solids are not free to move quite the same way that they are in a gas. Gases are less effective, though, than solids and liquids in transmitting vibrations. How well a gas transmits a vibration depends on the gas's temperature and density. Obviously, the more dense the gas is, the easier it is to transfer the motion. The less dense a gas is, the harder it is to transfer a motion. Okay, so if we remind ourselves of Newton's second law, for every action there is an opposite yet equal reaction. That can allow us to understand the two kinds of waves that we're going to discuss here. Transverse waves, which is a disturbance perpendicular to the motion of the wave, and longitudinal waves, which is a disturbance or a vibration parallel to the motion of the wave, and we're going to discuss this a bit further as we go through. So, a transverse wave is a wave in which particles vibrate perpendicular to the direction of the flow of energy. So, for example, water waves. A boat bobbing up on waves moves up and down. This direction is perpendicular to the direction of the flow of the energy of the water waves, which would be going horizontal. So, another example is when you strum the string of a guitar, you can cause the string to vibrate. The stimulus, or the origin of the vibration, provided by your finger strumming the guitar, is near one end of the guitar string. The vibration moves along the string and reflects at the far end, returns and reflects again, and so on. So, however, the guitar string does not move in the direction of the energy flow. The string vibrates perpendicular, so it moves up and down, while the energy flow is moving, left to right, up and down the string. And then we already saw the example of the boat in a previous slide. Let me just back up. So this is an example of a transverse wave. So remember that the boat is moving up and down, but the movement of the wave is left to right. So these are perpendicular to one another. Okay. And so that would be our transverse wave. Okay, so we can also see a longitudinal wave, which is a wave in which particles vibrate parallel to the direction of the flow of energy. Okay, so we can see that in this spring. So if you performed the activity where you pulled the string, you can create a longitudinal wave motion in a slinky. That's that toy that looks like the picture, and you start it at the top of the stairs, and then you can flip it over, and then it goes down the stairs by itself. That slinky toy. I'm not sure if we remember that from the 80s, but if you have that, then you can create a longitudinal wave motion by sending pulses along the length of the slinky. So a pulse is a single wave or single disturbance. So if we pull it back, and then it'll spring forward, and the direction of the motion of the pulse is forward, and we will see a number of these kind of bunchings as the wave moves through. So it'll bunch and then spread out as the wave moves through. So the scientific term for this is compression, and then as it kind of bounces back and decompresses, then we call this the refraction, and the whole thing is moving in the same direction as the energy is moving in the same direction as the toy itself. So unlike the boat, which was going up and down while the waves moved left to right, in this case the toy is moving in the same direction as the energy. So sound is a very important example of a longitudinal wave. So gas molecules have a much greater freedom of movement, and they are in constant motion due to their temperature. So a longitudinal vibration in a gas results in regions where the particles are close together, called a compression, similar to like we see on the spring on the screen, and regions where they are farther apart, called refractions. The term compression and rarefaction correspond to the local pressure differences as the wave's energy passes through the medium. When the particles are closer together or compressed, the pressure is increased above ambient pressure, which is just regular room pressure. The term ambient pressure describes the average pressure of a gas. the regions where the particles are farther apart have a pressure that is lower than ambient pressure. Okay, so we can kind of draw this out very similar to how we see on the screen, where we would have particles moving out and then very close together, and then out and then very close together, out and very close together. Okay. A vibrating object can produce longitudinal waves in a part of the medium that surrounds it. So if the waves have properties that make them detectable to the human ear, they're called sound. The energy transferred through successive compressions and rarefactions of a sound wave cause vibrations in our ears that the brain interprets as sound. Okay. Sound is also transmitted through liquids and solids. That's why you can hear through a wall or underwater. Our ears are less suited to detecting sound waves in liquids and solids. So think about it, if you're underwater, maybe you're playing in a pool with someone and they're trying to tell you something underwater, it's harder to understand what they're saying than if you're standing above the water. Because the longitudinal waves move better through the air than they do through a solid, which is why maybe listening through a door, your eavesdropping is mumbled, or underwater seems garbled. Okay. Here we have another and some official definitions of compression and rarefaction. So compression, the region in a longitudinal wave in which the medium's particles are closer together. And rarefaction is the region where it is further apart. So in this case, we have a tuning fork, and if we hit the tuning fork, then we're going to have sound that is going to move in a wave, and that means that we're going to have places where the particles are closer together and places where the particles are further apart. To summarize, in transverse waves, the particles of a medium move perpendicular to the direction of the flow of energy. Longitudinal waves, the particles of the medium move parallel to the direction of the flow of energy. In a fluid, longitudinal waves transfer energy through regions of higher and lower pressure. These regions are called compressions and rarefactions, respectively. Sound is an important example of a longitudinal wave. It is a form of energy produced by rapidly vibrating objects. And many wave motions in nature are a combination of longitudinal and transverse. So, to follow that up, water waves on the surface of a lake are largely produced by wind. The wind will impart some longitudinal motion to the water molecules, resulting in a motion of the water molecules that is an oval in shape. The shape of the oval is controlled by how much the molecules move in each direction. So we can think about this as this diagram. So if I have my waves, then the wind is moving this way, which is moving the water on the top. So this water is going this way, and then it's going to cycle back and come back to where it was originally. So if the perpendicular motion is much greater than the motion parallel to the surface, the oval is longer. Okay, so it'll be more of a, maybe more of this. And then we see that when the waves are really crashing, right? They're coming up very, very high and falling much lower. Another example of a complex wave occurs when you strike a solid surface with a solid object. So you strike a piece of wood with a hammer, for example. Some molecules are driven forward, initiating a longitudinal wave, and the intermolecular forces that connect the rest of the surface also create a transverse wave that radiates. So if I have my surface here, so I have my surface, and then I'm going to hit with my hammer. Okay, we're not going to mock my drawing skills here, but if I'm hitting downwards, then initially some of the energy is going to move that way, but then some of the energy is also going to start moving this way as the particles here all together vibrate and move some of that energy displaced to the left and the right. All right, we've reached the end of this lesson. Please be sure to complete the quiz below the lesson, and if you have any questions, please do not hesitate to contact your teacher.